Hello, my name is Fernando Guerrero. I'm from Airbus Cybersecurity, and I'm going to show you the risk analysis methodology that we used for the SeCoIIA project in order to define the misuse cases. This methodology is based on the IEC 62443 standard, and as you may see on the left-hand side, we have followed a five-step approach. Being the first one, the information gathering, so we had the interviews with the people inside the plant and inside the use cases. Then we went down to the high-level risk analysis, gathering what was most critical for the users and from the use case owners, and then went down to the detailed risk analysis, in which we analyzed the assets, what the risks for them were about. And finally, we created a result and went to a review with the use case owner. So all of that is performed during the risk assessment for the misuse case. And then we went to the attacker definition and staging, adding the risk assessment to the use case, meaning what risks affect to what assets within the use case. We then found some mitigations controls that were there and that should be implemented, what the limitations were, and with all that information, we identified the unmitigated misuse cases, and we translate all of this information into the meter matrix approach using the information control systems approach of that matrix. So now I'm going to explain the misuse case for the aerospace use case. As you can see, we started analyzing the misuse cases for the aerospace. You will see that we have a 4% high likelihood of high impact risks, and most of the risks that we found are located on the low parts on the green side, which won't be impacting much to the use cases. And then the second number of risks that are affecting this use case will be on the mid part, so you will see high impact but low likelihood of happening, and so on. So we have one example of internal employee and visitor could introduce malware through an USB device. You will see that for that risk, we thought that the impact level would be high, the probability will be high, and also the risk source for this one is physical access, meaning someone will go into the plant and will introduce the USB, which is already infected. It doesn't matter if it's accidentally or if it is on purpose, the risk just measures this up. Then the other example that we found is a distributed denial of service attack targeting the Kepler PC server on the national data lake to the Airbus Defense and Space in Spain network, and that would affect indirectly all the systems connected to it. This has an impact level of high, and the probability is also high, being the source of the risk, the access to the wireless LAN, and also access to the local area network. So with those risks and of course many others, the misuse case was defined. And the first misuse case that we have there is the insider threat and adversarial machine learning. And the stages that we found for this misuse case are as follows. So the introduction of this malware into the IoT platform operator software. So even either by USB or by a misbehaving human attacker from external networks or remote access, this malware is located into the IoT platform. Then the development of attacks between the server and the IoT platform. So now that the malware is over there, the attacker has access and starts creating the link between his control center and the use case. Third stage is exploitation of sensitive information, and that means that the attacker will get the configuration files, for instance, from the IoT platform, or alter those configuration files that will go into misoperation of the use case that will affect the whole supply chain of the final resources that are being manufactured over there, and will affect finally the results of the plant. And then the last stage will be the insertion of an advanced persistent threat using offensive machine learning on the IoT platform software, meaning all of this is being automated now. The malware is over there. The threat should be persistent in time and will be developing itself throughout these machine learning algorithms already present on the platform, and will keep affecting the plant unless something is done to avoid that. So as you can see, two misuse cases are associated with this scenario: misbehaving device and misuse case 2, misbehaving. And for that scenario and for those misuse cases, we established the capabilities and the controls for associated to those capabilities that are going to be used and that should be implemented. So as you can see, we started with the information security side. On the smart combined asset and user authentication, we have identity and access management for the systems and for the network, signature-based authentication for the devices when they talk with each other. Then for the IoT authentication and encryption, we thought about network hardening and a software baseline, so having an inventory to protect everything that is within the plant. On the process safety side of things, we thought about this collaborative SOC for distributed OT, which is part of the SeCoIIA project. So creating an OT security baseline, and with the industrial asset inventory, all of that information will be gathered into the collaborative SOC. Now we will start with the automotive use case. So again, as with the other use case, we started by evaluating risks. You can see already that a high number of risks are on the middle level of the evaluation, and we have an 8% of high likelihood and high impact risks that we found for this use case. We have set two examples over there for the whole scenario of attack. So one, an attack on the cloud connection, a man-in-the-middle attack, essentially, that will derive on a high impact and high probability, being the resource of the attack, the hacker. And then we also found that there could be a supplier connection that can be corrupted, that has an impact level of high with a probability high, being again the risk source, the hacker. So with that analysis, we describe two misuse cases, being the first one here. As you can see, a man-in-the-middle attack means that someone got access to the whole network and to the whole use case, and with that access, the attacker starts sniffing, starts watching what is going through the network, what is going through the business cloud inside this use case. And then he goes down to breaking the communication sessions within the cloud-to-cloud connection, meaning the suppliers are no longer able to communicate. The supplier and the R&D facilities or even the production plant are separately from the network, separated from the network and from the central business cloud. And then that happens, the attacker sets different connections to itself, and it identifies himself as part of the business cloud. The whole scenario reconnects again, nobody noticed, but then he starts intercepting or manipulating the contents, meaning damaging the keys, creating new encrypted keys, and so on. So at the end, the production plan gets information that it is not used to get, and the whole production line either stops or gets somehow affected. The second misuse case of this use case is about a Byzantine fall attack, which is essentially an attack that creates different responses on the whole cloud architecture. So someone get access via phishing email to the whole environment, and then it corrupts one of the instances within the business cloud. And as you can see on the right hand side, you have 3 instances of the cloud, for instance. So A, B, C start communicating. As you can see, A and B are sending and receiving X. So the actual keys, encrypted keys, and recognized keys of the use case. But whenever B gets corrupted, it starts sending a Y to C. So another encrypted key is something that is being changed, and therefore the whole cloud set collapses. And given the false data from the corrupted answers from one instance of the cloud to another, the whole system is interrupted. So in order to fight these misuse cases, for the first one, we found out that in the information security side of things, we should be working on data encryption and also signature-based authentication. And for the IoT authentication and encryption, we should be working more on network hardening and traffic encoding. And of course, human preparedness in order for the whole people working in this use case to be aware about what the risks are, what the misuse cases are, and how to not fall into the phishing scam, for example. And then for the Byzantine attack, a secure config cloud manufacturing backbone should be there. So a robust cloud architecture should be established, meaning the network interfaces, encryption, connections, inventories, and so on. And of course, also about awareness. So the administrators of the whole cloud environment should be aware of what to do, how to act, how to react if there's some attack or some issue, on what the actual encryption keys look like, and so on. Now we go into the maritime use case. So in this case, we have only 1% of the risks that are high impact and high likelihood, but there's a bunch of them also in the middle level of the risk assessment. We have 2 examples here: ransomware locks the PC, and network access compromise, both with high impact and high probability. One being performed by an outsider, and the other one being performed by the network itself. So the use case that we described for this maritime use case, you will see that it happens in 3 stages. So the first one, the introduction of malware into the industrial PC, one PC that's inside the plant. This malware gets introduced by a USB, a bad USB inside any of the industrial PCs, and then the infection happens. The industrial PC is already filled with malware or access to attackers. And then the software gets compromised, and establish an easy link, let's say, between the attacker and the plant. And this, of course, can happen from the internet in any moment, but could also happen from a supplier inside the robot itself when the connection for remote support is enabled. So for this misuse case, we define the following controls within the capabilities. For the fine-grained access control, we thought about limitation of internet surface. Of course, that means configuration. That means knowing what interfaces are over there and what should be enabled when. Then for the process safety, we thought about the IDS that is being built on the collaborative SOC for distributed OT, and the restriction of the use of USBs within the plant. That is, of course, a more administrative control, but should be there. That doesn't mean that there won't be any USBs in there, but that the control of the usage should be in place, documented, and logged out. We have another use case in here, the cross-sectorial. We found no high impact or high likelihood risks, but we did found several risks that were in the middle level. And one of them is, for example, the changing configuration of the robot via a web server. This has a medium impact, but a very high probability, and an attacker could be any attacker type 1 or script kiddie. So the misuse case is configured as follows. The network and offensive AI when insider attack comes in place, and for that there is a first, of course, information gathering, get to know what the network looks like, what the devices that are operating over there are configured, and so on. Getting to know the information about the plant and their suppliers, etc. Then the attacker starts gaining access by inserting false training data to the robot or by breaking a wireless communication on the robot, so exploiting its own capabilities to make some damage. After he has some access to the network, then he starts compromising the robot itself through the distributed misconfigured AI algorithms on the robot or by direct manipulation. So he will send scripts to the robot and starts teaching the AI how to misbehave, or either just access the robot itself and change the configuration files within the robot so the robot starts misbehaving. And finally, the attack performs or starts achieving its objectives by causing damage to the robot itself and causing damage to the production line, or even creating some safety issues with the workers within the plant. And for this misuse case, we have established these controls. So for safe and secure collaborative robotics or robotics within the use case, the robot software baseline should be established. So the configuration files, even if they got changed at any moment, then everyone or the administrators know how the baseline looked like and can go back whenever they need to. Then the cognitive and emotional behavior analytics. For that, we have some security measures in the robot settings, so users and passwords, encryption of the configuration files, and so on, so that the changes that can happen are not very easily done. And finally, in the collaborative software for distributed OT, we have this host-based IDS, meaning a protection within the robot itself, and it can send alerts to the SOC and say, hey, I'm being attacked, please help, so someone can go there and perform the mitigating actions. So as a summary of the whole risk assessment, as you can see, we have found several sources of risks, and we cannot say that there's a pattern here. So you can see already that for each use case and for each industry, the sources of risks are different, even though for maritime aerospace are kind of similar due to the nature, let's say, of the plants. But then for automotive and robotics, we found out that most of the risks were coming from different parts. So for the automotive use case, it has to do with the cloud, the hardware, and the human interaction are mostly the major risk sources. And for the robotics use case, mainly the human is the one that is going to be the basic or the major source of risk. Then we also found out what the mitigations look like in order of technical or organizational. So as you can see, for the cross-sectorial, meaning the robotics use case, you will see that all of the proposed mitigations are technical, and of course we are mostly using the robot for the use case. So I think it's basically that all the controls are in there. But then for the other use cases, we also have organizational mitigations, meaning administrative procedures, also connections within the policy makers and the policy systems and the access control systems into the plant. We also have technical mitigations for all of them. So all the misuse cases can be controlled in somehow from these two realms. So that's it from my side, and we'll continue with the architecture of the whole SeCoIIA project and its definition. Thank you.